So we've already talked about how glycolysis is going to take glucose and break it down into pyruvate. Then we spend some time looking at how pyruvate, with pyruvate dehydrogenase, gets changed into acetyl-CoA. Then acetyl-CoA enters the citric acid cycle, also known as the TCA cycle, or the tricarboxylic acid cycle, also known as the Krebs cycle. That then produces a lot of NADH. Those extra electrons now are going to go into the electron transport chain, where protons will be pumped across the membrane, those creating a proton gradient. Those protons will then go back through an ATP synthase with oxidative phosphorylation. So right now, we're in the electron transport portion. What's going to happen in here is there's a set of enzymes that are going to be passing those electron carriers through. So we're going to go through each one of these in turn to discuss what's happening here. Notice that in this case, bacteria do also do this, but bacteria don't have a separate organelle for this, so instead it occurs across the cytoplasmic membrane. So I want to use this slide to take a closer look at where things are happening. So all of these enzymes are actually in the inner membrane. So if you'll notice in the mitochondria, there's an outer membrane as well as an inner membrane. These enzymes are actually taking place in the inner membrane. They're actually pushing electrons out into the intermembrane space. That is the space in between the membranes. So that intermembrane space is where the proton gradient is being built up so that then those protons can rush back into the very center of the mitochondria. So when we look back at this slide, you can now see that all of these proteins, most of them are membrane bound. So that blue line in the middle is supposed to be the membrane. Then you have that inner mitochondrial matrix on the bottom half and the intermembrane space on the top half. So again, those protons are being pumped into the intermembrane space from the mitochondrial matrix. Then when the proton gradient is set up and then you have this ATP synthase, the protons are then moving from the intermembrane space back into the inner portion of that mitochondrial matrix, into the very center. For those of you who haven't had a biology class in a while, the mitochondria does have its own genome and its own ribosomes. But most mitochondrial proteins are actually synthesized in the cytosol and then imported into the mitochondria. So just that note that the mitochondrion does actually have its very own genome, which is, you can do some really interesting genetics since the vast majority of all the mitochondria come from the female, because eggs are really enormous and sperm are much, much smaller. So sperm really just basically have a small little coat to carry a whole bunch of DNA and enough energy to move that flagella and go. So eggs are the things that actually usually have all of the stuff, including your mitochondria. So that genome actually is a way to trace back maternal lineage. Since we're talking about electron transport, we also need to spend a lot of time on reduction potential, as well as some of the calculations that go into this. So a standard reduction potential is a quantitative measure of the tendency of a chemical species to be oxidized or reduced. So we spent some time before talking about oxidation, which is the loss of electrons, and reduction, which is the gain of electrons. And remember, anytime we have a redox reaction, we're going to have both of these things taking place. We're not going to have electrons just floating out into the mitochondria or the cytosol or wherever we are. So whatever is going to be oxidized, there has to be something to be reduced along with it. Those electrons have to go somewhere. We've also spent a fair amount of time talking about our standard free energy for these. And so we can still talk about standard free energy for a reaction now along with the standard reduction potential. In order to do this, we're going to need a few things. So the nice thing is that the standard reduction potential is very closely tied to the standard free energy, but we need a couple of factors to make these two things equal to each other. The first thing that we're going to need is N, which is going to be the number of electrons. Some of these will be 1 electron transfers, some will be 2 electron transfers. In the real world, when you're looking at a wider variety of elements, you can do more than that, but here for biochemistry, we're going to be dealing mostly with 1 and 2 electron transfers. The other one is F, which here is Faraday's constant. Depending on what other reference sources you're looking at, sometimes that's a pretty cursive, italicized F. Here, just to make life easier, it's just done in rather plain script, but a capital F, which is Faraday's constant. So that is a constant. We'll look at the value for that later, but it's just a number to plug in. The other thing to notice is that this is the change in the standard reduction potential. So in order to get the change, we're going to need the difference between the donor and the acceptor. Since the goal is to look at the change, we therefore need the standard reduction potential for an acceptor for a donor. There's a lot of different ways to calculate this. At the end of the day, the easiest way to look at it is that it's the reduction minus the oxidation. When you do it this way, all you have to do is pull the numbers off of the table. So you don't do anything fancy to the numbers. You just say one of these is the reduction, that's the first number, and I'm going to subtract my oxidation. You are going to keep then whatever signs are on the table. There are different ways to do this. I usually actually do this differently in Gen Chem 2, but we're not in Gen Chem 2, we're in Biochemistry 1, so we're going to go with this formula. If that change in the reductive potential is positive, electrons are then going to flow from the donor to the acceptor. This is going to correlate with a negative standard Gibbs free energy, or that being something that will go in the forward direction. If you'll notice back from this slide, there is that negative sign. So realize that when we have a negative standard free energy, that's usually an indication that something will drive itself forward. Because of that negative sign, it's going to be a positive change in standard reduction potential that will drive the reaction forward. There's a lot of different ways to look at which one should be which. So we'll talk about this a couple different ways. To start off with, the redox couple with the more negative reduction potential will donate electrons to the couple with the more positive reduction potential. So there's an example written below here just to look at how you can break reactions down. So this actually has ethanol, where ethanol then is oxidized, and then hydrogen, which is then being reduced. When we're talking about something that's going to have a more positive and more negative reduction potential, what I want you to do is take a look at the chart that's there on the right. What you'll notice with this is that things that are closer to the top of the table are things that want electrons. So fluorine would love to be negative, would love to have those extra electrons. So it has a positive reduction potential. Fluorine is chemically more ready to accept electrons. At the opposite end of the spectrum, you've got a lithium ion. Lithium can accept electrons, that lithium ion, it can. But lithium, from a chemical standpoint, really does a lot better as a positive ion. When you look at it on the periodic table, it's in that top left-hand corner, being an alkali metal. So lithium would really rather not actually gain electrons. It's not really a thing lithium wants to do. So you can make it do that, but lithium's going to have a negative reduction potential because lithium doesn't want those electrons. You can force it to do so, but it's not going to be happy about that and therefore has a negative reduction potential. In the next video, we're going to take a closer look at some examples and a closer look at what a table of standard reduction potentials is going to look like in biochemistry.